slope stability, and factor of safety calculation. Okay, here is the outline. First, I will talk about the strength reduction method, and I will demonstrate some examples to calculate factor of safety. And in the end, I will have 2 case study application using this method. Okay, first, factor of safety in geotechnical engineering. In these slides, we can see the classical Pareto solution. This is actually a shallow foundation capacity calculation. So using FLAC3D, we can simulate the load here versus the displacement, which is actually the settlement of the foundation. Okay. We can see at the beginning there's a linear response, and then the load became curved. And at some displacement, the capacity became saturated. Okay. So this capacity is close to 5.1. Okay. The factor of safety usually is some number greater than 1. Okay. For example, if we assume that factor safety is 2, that means we only use half of the capacity during the design. Yeah, we reserve some extra capacity for safety purpose. So this is generally the definition of factor of safety. So in this case, we can define factor of safety is a load capacity over acting load. Okay. Of course, the load can have different measurement. For example, force, moment, or pressure. I will talk this later. Okay, this is another example for factor of safety calculation for retaining wall. We could have multiple definitions of factor of safety. For example, we can define is some ratio between the moment. Okay, we can also define it as the ratio of some forces, or we can define with them. We can define the factor of safety with some overcharge force ratio like this. Okay. Okay. This is another examples for slope stability analysis. In this case, we can also define the factor of safety is a overcharge load Q over the acting Q. Okay. And we can also define the factor of safety, for example, the unit weight ratio. So in general, factor of safety can have different definitions. It depends on how you define, factor of safety. Okay. In these slides, it shows some, the factor of safety calculation in the classical method. Maybe have, depends on how we define the failure mode. For example, the first one, we assume that the failure will along the curved path. And in the second figure, we assume that the failure along a straight line. Okay, so that means factor safety definition also may be related to the failure mode. Okay, and factor safety is also related to what is the factor safety is also related to different definition. That's the general idea. So alternately, we have another method called strength reduction method. For example, we assume that the material follows the Moore-Coulomb law. Okay, so this line is a shear failure line. So we can define the factor safety is some ratio between the cohesion. That means we have a real cohesion, and then we assume a reduced cohesion, and then to check the stability, and then the factor safety is a ratio between these two cohesion. Or we can reduce the friction angle. For example, we can define the factor safety is a tangent friction angle. Okay, and then so this factor safety relate by the reduction of cohesion, and the factor safety based on the reduced friction angle may be different. So we can also reduce cohesion and friction angle at the same time. For example, we define a variable is cohesion plus sigma multiple tangent phi. We can reduce this variable and then calculate factor safety. So in this way, if we assume that the material is Moore-Coulomb model, actually we assume that the apex will keep constant, and then we just rotate this line around that apex. So this method actually reduce the cohesion and friction angle at the same time, and the ratio have this relation. Okay, C over C reduced cohesion equals to tangent friction angle over tangent friction angle with reduced friction angle. So in this way, we just assume that the factor safety by reducing cohesion and by reducing friction angle is the same. Okay. So this slide is the method based on the limit equilibrium method. So for this method, we first assume a failure mode, and then we divide the slope above this failure line with many slices, and then we assume some forces interaction between these slices, and then we take care of the global equilibrium, and then can calculate the factor safety. This method is quite popular a long time ago, before the finite element and the FLAC became popular. So we have right now the alternative method called numerical modeling approach. So based on this approach, a full solution of the coupled stress, displacement, equilibrium, and constitute equation is made with code like FLAC or any other finite element software. So given a set of property, the system is either found to be stable or unstable. Okay, by performing a series of simulations with various properties, the factor of safety can be found that corresponds to the point of stability. And this approach is much slower, but it's tolerable, but much more general, okay, than the equilibrium, than the limit equilibrium solution. So only in the past few years has it become a practical alternative to the limit equilibrium method, since computers now became faster and faster. So here is a comparison between these two approaches, namely numerical solution and limit equilibrium solutions. So we compare different atoms, for example, for equilibrium, and the numerical solution satisfied everywhere, and limit equilibrium method only satisfied for specific objects. For example, only satisfied for those slices. And for stresses, numerical solution computed everywhere using field equations. And limit equilibrium method computed approximately on certain surfaces. For deformation, it's a part of the numerical solution, but it's not considered in the limit equilibrium approach. For failure, numerical solution satisfied everywhere for the yield condition, and the failure surface develop automatically as conditions dictate. And for limit equilibrium method, failure allowed only on certain predefined surfaces, and no check on yield condition elsewhere. For kinematics, the numerical solution, the mechanism that develop satisfy kinematic constraints. And for limit equilibrium, kinematics are not considered, and the mechanisms may not be feasible. Okay, so how to using the numerical approach to calculate factor safety? Okay, first, for a single numerical solutions with given properties, we are show either failure or stable. Yeah, and how do we get the factor safety? So we can run several simulations and with different properties. So the different properties just follow some reduction method. For example, the popular way is just reduce cohesion and tangent friction at the same way, at the same factor. So how can the exact value of reduction factor be found quickly with the smallest number of simulations? So we attached a paper by Dawson, etc. So in this paper, they gave the bracketing method. So generally, we repeated halfway between stable and unstable, and then every time we just half the reduction factor between the previously calculated ones, and eventually, this method will convert at some small intervals, and at that is a reduction factor we try to obtain. So we will have some more details, in the next slides. Okay. So in FLAC, this is the steps these are steps in the strength reduction solution. First, we determine the characteristic response time of the system in terms of steps needed for equilibrium. We call it NC. Okay. The next, we say that the factor is 1 and keep halving until lower bound is found. So we call it Fs. So generally, if f equals to 1 is not stable, and then we just make it half. If still unstable, we just make it 1/4. Okay, this is one direction. We can also have the other direction. Yeah, we can keep doubling f until upper bound is found. So we call it fu. So once fs and fu are found, we set f, a new f, just half of that two values, and then so on and so forth. And then we can determine, eventually we have a converged f. Okay. So next, just so we have multiple calculations. Each calculation will have either stable or unstable. So how to determine that calculation is stable or unstable? So actually this condition is determined, is program specific. Okay. For example, in finite element, usually they're based on implicit matrix solution. And then the condition of instability is often based on the non-convergence of the system of equations. But in FLAC, instability is determined by monitoring the kinetic energy in the method. And this is measured by the unbalanced force ratio. Okay, here is just we talk about specifically in FLAC how the stable and unstable is determined. Okay. So first we do up to n characteristic steps and see and record unbalanced force ratio RU. So if RU falls below some value, for example, 0.01 in 2D and 10 to minus 5 in 3D during stepping, and then make labeled as stable. And if RU, the difference between two RU and relatively ratio less than 0.1, okay, we just label it as unstable. And if total iteration is greater than 6, and then we also call it unstable. And then we have some iteration and then go to step 1. Okay, using this way, we can calculate the factor safety in FLAC or FLAC3D. So here is a validation examples. So for this slope, the slope angle is 45 degrees. If we have these specific properties, and then theoretically this slope stability is close to 1. So we will check the FLAC3D result later. Okay, here is some old figures calculated by FLAC version 4. Okay, and then different grade will have a little bit different result, but generally the calculated factor safety are very close to 1. Okay. So before I talk about these slides. Let's go to the exercise folder. We open this FOS project by FLAC3D version 9. So in these examples, we have several testing. So first, let's run data file. So we can see that in the first step, the characteristic step is 1395. Yeah, and then they assume the factor is 1, and then 2, and then 1.5, and then 1.25, and then so on and so forth. So in this figure, I show the contour of maximum shear strain. And generally, let's go back to the unstable save file. So in this figure, we can see that the contour of maximum shear strain is very, looks like a sliding surface. Okay, and then if we plot the vector of velocity, so we can know that the material above that assumed about that sliding surface represented by the contour of maximum shear strain, have just move downward, along the sliding surface. So and from the information windows, we can see that the calculated factor of safety is 1.03. Okay, it's very close to the assumed 1. Okay, for this testing, we assume that it's a associated method. So we can also try the non-associated approach. So for associated method, we assume that dilation angle always the same with friction angle. But for unassociated, we can define the dilation which can be different from the friction angle. For example, I assume that the dilation angle is 10, but in the model, the friction angle is, where it is? The friction angle is, let's move this window a little bit. Okay, the friction angle is 20, okay? So now we assume that dilation angle is 10. Let's rerun this again. Now factor is 1.5. Now 1.25. 1.125. 1.063. 1.031. 1.1. 1.016. 1.023. So we can see that now the factor safety is 1.02, a little bit, less than the associate method. This is reasonable because we have a lower dilation angle. and then the higher dilation angle will have higher slope stability, because dilation actually is the effect of some interlocking between material. Yeah. To show the contour of the maximum shear strain, we always click to some unstable save file, for example, this one. Okay. So the next test is using the blanket method. But sometimes we already know that the fact safety is, in some range. For example, this one close to 1. So we don't need to using the general way between 1 and 2 or some other values. We can directly assume that using a blanket range, for example, this one, I can assume that the blanket is between 0.95 and 1.1. So using this blanket, maybe the calculation time will be smaller than the previous one. Let's check this from this data file. So first, they assume 0.95, and then 1.1, and then some value between them. Okay. Okay. You can see that the fact safety is 1.02, and then I think it's faster than the method 1. Okay. Okay, next testing, we will refine the grid to see how the fact safety would be. So generally, I turn on this, and I using a refined size. Okay, I just change the S to 4. Okay, let's run this data file. So since the grid is refined, and then more calculation time is required. Theoretically, if the grid is more refined, the fatal safety should be smaller, because the width of the localization is smaller. Yeah, and then the failure rate will be bigger. Okay, so the fatal safety should be smaller. So just look at the calculation. The characteristic step right now is 3356, which is almost double than the previous one. So the current reduction factor is 1.02. and then current one is 1.015. Okay, here is the result, and then here is the figure. Okay, we can see the factor safety is 1.02. Now a little bit less and less than the first one, 1.03. Okay, so sometimes if we don't know the factor safety, we can using the command list FOS. Okay, and then we can see that the actual factor safety is 1.015. Okay, but in our report, it's less meaningful have a the 3-digit factor safety 1.015. That's not that's not meaningful. Usually we only report the only 2-digit after the point, for example 1.12. Okay, so let's go back to the slides. Okay, this slide just summarizes the advantages of using a numerical factor safety calculation. First one, any failure mode develop naturally. Okay, for example, this one, if the slope have some weak planes, this method will automatically calculate if the failure along this weak plane or some other path. Okay, we don't need to assume the failure mode at the beginning. Number two, there are no restriction on geometry. So all situations, slopes, footings, tunnels, etc. are modeled in the same way. Okay. Number three, no artificial parameters needed to be given as input. For example, the functions between interslices, what force angle is horizontal or along the slope angle or whatever. So we don't need to assume this slice force angle. Number four, multiple failure surface can involve naturally. So I think we have an example in our documentation. Okay, and number five, structure interaction is modeled realistically as fully coupled deformation element, not simply as equivalent forces. And number six, kinematic is respected. Okay, we know how the material above the slide surface will move to which direction. Okay. Okay. How about the disadvantage of using the numerical factor safety solution? I think maybe just only one, maybe speed, and but generally I think it's acceptable using this method because compared with the advantages, the speed is just a minor disadvantages. Particularly in nowadays, computer becomes faster and faster. I think this would not be considered disadvantages nowadays. Okay. So generally, there's no real drawback. Okay. So next, so you may ask a question, what model can have automatic factor safety calculation in FLAC and FLAC3D? And so far, the built-in model with the factor safety calculations are Moore-Coulomb, number one. Number two, ubiquitous joint model. Number three, Higgs-Brown model. So the new model, columnar result, that's actually a multi-jointed model. And, that's new in version 5, can also have this built-in procedure. And the interface also automatically have the built-in procedure. For any constant model does not have the built-in procedure. So we can use in the similar way, by manual steps. For example, for some material with one property, we can manually reduce that property, and then we do multiple calculations, and we record some characteristic, for example, displacement at some point, and then we just plot that displacement versus the reduction factor. Okay, if we see that a sudden increase, for example, in this figure, the displacement suddenly became increased at some point at 1.22. And then we can consider that the factor of safety is 1.22 based on the reduction of this property. Yeah. So generally, we can have the built-in procedures for some quantity models, or we can manually using the similar steps by other quantity models that not have built-in procedure. Okay. Here is a example number one. This example actually already included in the documentation. So we can use this method to back calculate the acceptable slope angle. So for some design, slope design, we don't know the slope angle. So we're using FLAC3D to calculate multiple cases with different slope angle. Okay, and then for each slope angle, we calculate the factor of safety, and then we plot the series pair of factor safety and the slope angle. So we have the curve like this. So for factor safety equals to 1, which corresponds to a slope angle, I think is close to 43 degrees. So we now know that the slope angle should not be greater than 43 degrees. Otherwise, the factor safety will be less than 1. Yeah. So generally using this method is very convenient to do some slope angle design. Okay. So this second example, I think is also included in the documentation. So we can plot the factor safety contour in FLAC3D version 9. So the method is just very simple. In the command of model factor safety, we just use the keyword bracket limit. For example, for this one, 0.5. Okay, and then the software will calculate each reduction factor with a difference of 0.05. And then at the end, the software can plot which part is stable and which part is unstable based on different reduction factor. So we can plot the factor safety contour. Okay. Next, I will took two case studies. The first one is Los Angeles Alameda corridor. So this is a picture of this project. It's a 10 miles long corridor, and they have 33 foot deep and 51 feet wide, and it's located in somewhere close to downtown Los Angeles. So these are the trench staged construction figures: stage 1, stage 2, stage 3, and stage 4. For stage 1, it's some excavation, and the stage 2 have a supported by a beam. Okay, and the step 3 is keep excavation, and this stage is critical. And then stage 4 have another reinforced beams at the bottom, at the middle of these sheet piles. So we need to determine the factor safety during the stage 3. Here is some picture on the construction. So we can see the beams at stage 2. Okay, I think this is a stage 3 construction, and this another figures on the reinforced beam on the top. So using FLAC, the factor safety include soil structure interaction, producing factor of 1.3. Okay, using limit equilibrium method predicts failure, which would result in over design of pile length by up to 8 feet. So using FLAC analysis resulted in cost savings of several millions dollars. Okay, because FLAC-D consider it safe, and the limit equilibrium method consider it's not safe. Otherwise, we should increase the pile length. Okay, and this another case study. So you can see, you can check the details in this paper. So this is some complex geotechnical conditions and the pressure distributions at the field. Okay, this is a typical cross section of the landfill, and we have field and a landfill cap, and here we have slurry wall, and we have some layers called valved clay. That's the critical material in this cross section. So this is the material property. Just pay attention to the valved clay. So they have various cohesions. Okay. So these are weak valved clay layers. Okay. Using limit equilibrium method with slurry wall, and the factor safety is close to 1.04, which is actually very close to 1. Okay. Consider the uncertainty for the conditions. This means the failure would already happened, or to be happened, or is marginally happened. Okay. So if we just assume some simple distributions of pore pressure using strength reduction techniques, so the shear strain rate contour just plotted in these two figures, and then they calculate the factor of safety only 0.91 for the existing slope, and if consider the slurry wall and the factor of safety even smaller and close to 0.43. So if the assumption is correct, this slope should already failed. Yeah, but on the side, the slopes are very well. So what's reason behind them? Okay. So some further investigation were performed. The reason is that the pore pressure distribution. So let's go back to the cross section. We can see that we have the evolved clay layer and we have the sand layer here. Yeah. So the pore pressure distribution is not follow the static equilibrium distribution. So we should calculate the real pore pressure distribution. Since they have a sand layer, the pore pressure here is much smaller than the static distribution. So which means that the effective stress around that low pore pressure area should be larger. Okay, and for the cohesion of the evolved clay usually is proportional to the vertical effective stress. Okay, if we assume that cohesion is 0.16 of the effective vertical stress, and then we recalculate the factor of safety using the strength reduction method, we can calculate that the factor of safety is 1.66. Okay. Even we consider the effect of the slurry wall, the factor of safety still have 1.38. So this is consistent to the observation on the site. Okay, due to the non-static distribution of pore pressure, the slope, some layers have higher effective stress, and the so have a higher cohesion. So the slope stability is actually stable. Okay, this is another case study. Okay, at the end, here is a bonus, and you can download FLAC slope version 8.1. So this small software is totally free without any constraints. Okay, you can download and use this software freely. Okay, thank you very much for this training of slope stability. Thanks.